Hey guys, how's everybody doing? Let's see, where's my microphone? There we go. Anyway, so today what I wanted to talk to you guys about are Hermite polynomials, and these sort of continue on this stream, on what we did last time in the stream, which was like several months ago at this point. And Hermite polynomials are related to Hermite functions, and Hermite functions themselves are eigenfunctions for the Fourier transform. So today I wanted to sit through and just work through some properties about them, try to get some exercise doing this stuff, and yeah, we'll see how this goes. So I've been teaching this class in tomography this semester, and in tomography, I mean, the Fourier transform is paramount. I mean, it's how you do a filtered back projection, which inverts the sinograms into an actual image, and so it is probably like one of the most important aspects of computed tomography. And Hermite functions have this nice relationship with both radon transform and Fourier transforms. I don't know how much I'm going to talk about the Fourier transform aspects of it today, and probably do that next time. Going to try to do a stream next week around the same time, but we'll see. Last semester, I live in Tampa, and we were hit by 2 hurricanes in the middle of the semester, and sort of like destroyed all that, and so I was just scrambling to try to survive teaching and everything. Roof needs repairs and all these other things, and so it's been hard to do anything with YouTube, and so yeah, and so I'm trying to get back into it, and so today we'll see how this goes. This stuff I'm doing is stuff I teach in my class, and as we go through it, we'll see how well I actually remember the proofs as we go. So Hermite functions, and I'm looking at the whiteboard over there because it's cueing me. But yeah, all the stuff with Hermite functions, stuff like that, I proved it like 3 weeks ago, and it's funny how things just sort of fall out of your head. So we'll see how we can do this, and I have my notes on my screen over here, and so a combination of my notes and and my wit. Hopefully we'll get through this. Okay, so if you guys are ready, we can go ahead and get started. And so yeah, let's do it. And if you guys have any questions throughout here, just let me know. While I'm up here at the whiteboard for a minute, I won't be able to see chat, but I'll be back in a second. So yeah. All right, so this is our objectives. So so we have Hermite functions, and so we have the Rodriguez formula. This is basically what I'm running with as far as our definition. And so this is why I find sort of the easiest to work with. You could start with sort of their orthogonality over here with like some sort of normalizations to put in here on top of it. But so you could start here and then get to here, but I find that starting here is probably the easiest to get through everything else. So, so our objective is to start with the definition. Then we'll get down to the recursion formula, and we've discovered this recursion formula by taking the derivative of hn of x in 2 different ways, and then we can use this recursion formula to come up with this formula for the generating function, and honestly we can just jump from here to orthogonality, so maybe we'll just do this one first. Again, let me know if you have any questions or anything else like that, or if the stream isn't working, or anything. So just let me know. So our objective here is to demonstrate this recursion. So the recursion is on the whiteboard, and I'm going to do it in a slightly different notation, slightly different index. So hn of x, and we're going to have this as 2x times hn minus 1 of x minus 2 times n minus 1 hn minus 2 of x. And so this is what we're trying to demonstrate. Okay, so in one case, we have just our usual sort of differentiation that we can do. So what we can start with, and so using this Rodriguez definition, so we're going to have hn of x is already given as -1 to the n of e to the x squared times d by dx to the n times e to the minus x squared, right? And so, I mean, if it's not clear that this delivers polynomials, I mean, we can actually probably work this out in a couple of different ways to demonstrate that. So what I can do before we jump into this, let's actually just verify that these are polynomials. Sorry, I am a little disorganized today. We'll get to this in a minute. Let's just go ahead and start with this. So moving this up here, and let's take a look at the first one. So h of 0 of x, I was just so excited to talk about this recursion. I just keep thinking like, oh, I have the proof of the recursion in my head. I need to get that to you guys. But I think I should probably cool it, and let's start with basics. So let's verify that these actually do give us polynomials. And I can actually do this for the first couple, and then if we want, we can actually go ahead and just see if just by the on the whiteboard over there, we can see that we have a recursive formula that just multiplies by 2x, and then also a constant for the two previous ones. And this recursion formula, if it holds, that would just produce polynomials throughout. But it's kind of easy to intuitively figure out why this would be polynomials. And so if we just go ahead and take a look at the 0th term, well, that's not too bad. So it's -1 to the 0 e to the x squared times the derivative of order 0, so we're not actually taking a derivative, times e to the minus x squared, so the Gaussian. And so when you put this all together, boom, this just gives you 1, because e to the x squared cancels e to the minus x squared, and that's nice and easy. Now if you want to start doing something more interesting, you take a look at h1, and so it's going to be -1 times e to the x squared. Now, this -1 to the n out on the front of this definition is really there to just make sure we keep getting positive coefficients, and because it's just awkward to get negative coefficients and things like that, and we want to use this in a variety of tasks. And so we put this -1 to the end there to cancel out what we're about to see here, which is going to be the first derivative of e to the minus x squared. So the first derivative of this guy is really just going to go ahead and it's going to pop out a -2x out of the Gaussian. So we end up getting that. And then we have this term here. We have this term here canceling this term here. And so we're left with just 2x. And so you see that basically what's going to end up happening is we're going to end up, this derivative here applied to e to the minus x squared is going to pop out some sort of polynomial that's going to come from the derivatives of e to the x squared and the chain rule, so it's going to give you a -2x each time. And then we're going to have product rules and other things, and they're just going to sort of mash together in a bunch of different ways. But all these monomials that we're going to end up getting out of here, that each one's going to have an e to the minus x squared attached to it. And so this guy's going to distribute through, and it's going to cancel those guys, and you're just left with a polynomial. So we can see that with h2 of x, and then we'll stop with our examples. So this ends up giving you -1 squared e to the x squared times the second derivative of e to the minus x squared. And so this is going to give us 1 times e to the x squared, and then let's take the first derivative. So it's going to be -2x e to the minus x squared. And then after this first derivative, now we need to take the product rule. So e to the x squared d by dx. Taking derivative now. And so we're going to have -2 times e to the minus x squared. And then we're going to have -2x times -2x times e to the minus x squared. Boom. And putting all of them together, we get e to the x squared times -2 plus 4x squared, and all of this times e to the minus x squared. And these two guys end up canceling, leaving us with 4x squared minus 2. So that's pretty nice. So those are our examples. So Hermite polynomials, obviously, as we take this, as we increase our index, we're going to have a matching increase in the power of the polynomial. So the 0th polynomial corresponds to a 0-degree polynomial, or just 1. And we have our first-degree polynomial corresponds to 2x, and our second-degree polynomial corresponds to a second-degree. Our third Hermite polynomial corresponds to a second-degree polynomial. So, okay, so that's what these Hermite polynomials are. That's what they look like, and what we'd like to do is we'd like to start proving some basic arithmetic about them, some tricks and ways of working with them that doesn't involve necessarily taking a derivative every single time, because that gets to be kind of annoying. And so what we're going to do then is we're going to go ahead and try to start with this recursion formula. And the recursion formula, as I have written on the board, is hn of x is equal to 2x times hn minus 1 of x, and then minus 2 times n minus 1 of hn minus 2 of x. And now the whole game of this is, we're hunting for this Rodriguez definition, where we basically have where we have the exponentials and derivatives and all that stuff tied in here, and we're going to try to sort of match whatever we can as we go through and try to put this together. So what I'm going to do, and probably the best way to start, is just by taking a look at the derivative of hn of x, and it's going to pop out a bunch of stuff. And it pops out stuff because, well, we have 3 different terms here, and that means we have a whole bunch of chain rules that we need to worry about. So let's go ahead and do that. So we're going to have the derivative with respect to x of -1 to the n, and then this times e to the x squared times the derivative with respect to x to the nth power of e to the minus x squared. And so when we take the derivative here, we're just going to go ahead and we're going to basically have a product rule coming through. So we get -1 to the n, and the first term is going to be 2x e to the x squared, and then we leave the second one alone, so d dx to the n e to the minus x squared. And now we have minus 2x time, well, let's take this one step at a time. So plus e to the x squared, and then we're going to have minus, no, we're going to just, let's do this, d dx to the n plus 1 of e to the minus x squared. And that's what we'll do. Okay, so now we have this, and so we're going to start hunting and looking for our Rodriguez formula again throughout here. So what we can see is that this piece here is basically the nth Hermite polynomial coming back out, and this one here should be the n plus first one. And so we can go ahead and write that out. So the nth one comes with a -1 to the n, so that's going to absorb that piece. So it's going to be 2x hn of x. And the second piece, well, we have this -1 to the n term, which is nice and all, but this is going to be attaching over here, and but we would want n plus 1, so I'm going to flip the sign on it, and so it's going to give us a minus hn plus 1 of x, right? And so already that's sort of a recursion formula we have. It's not a great one, but we can see already that hn plus 1 is equal to 2x hn of x minus the derivative with respect to x of hn of x, right? So sort of putting this whole equation together. And so that's one thing we got. So that's not what we want, though. What we want is we have this 2x. So the theorem basically says that we want 2x here. We have a 2x there, which is great, but we don't have the constant times hn minus 2, and so we want to be able to sort of replace that here. So that's something we're going to have to work out. And this is kind of the more annoying route that we can take. So what we can do is we actually can do the same sort of thing, and I'm going to call this equation star, and we're going to move on and take another way of looking at this. And so instead of converting that to hn plus 1, we're going to convert it to something else, and then we're going to get a second identity for the derivative. And so what I'm going to do then is I'm actually going to go ahead and I'm going to take one derivative here. So this becomes -1 to the n, and we have 2x e to the x squared times d by dx to the n e to the minus x squared. And then we're going to have plus e to the x squared. And we're going to have d by dx to the n. And we're going to have minus 2x times e to the minus x squared. Okay. And in doing this, we actually have now introduced the second term in with our e to the minus x squared. Now we have a minus 2x there. So what you can do, and this is what makes it annoying, is you can apply the product rule n times. So we have n derivatives, and so the idea is that we wanted to sort of distribute this and use this rule over and over again. And so what we end up getting is -1 to the n. We have 2x e to the x squared d by dx to the n e to the minus x squared. And this becomes plus e to the x squared. And now we end up getting this. So it ends up having like a choose statement. So it's going to be k equals 0 to n. And we're going to have n choose k. And then we're going to have d by dx to the kth power attacking minus 2x. And then we're going to have d by dx to the n minus k power attacking e to the minus x squared. All right, and right now parentheses, I think that's good. Okay, so this is when you have a slight panic attack and you're like, I'm not going any further, and you just like want to run away from the equation. Having a choose statement inside of this thing that already involves a ton of derivatives and other things like that, you're like, there's no way I'm going to take n minus k derivatives of e to the minus x squared. That's a job for somebody else to do, or a computer to do if you have one that can do it. But then you take a closer look and you see that the derivative here, the derivative of k times to the minus 2x, well, actually, minus 2x is just a linear function. After two derivatives, it's gone. And so we can actually change this from being from k equals 0 to n to k equals 0 to 2. And that's a lot easier to deal with. So let's start working that out. And so what you end up getting is this. You have -1 to the n. You have 2x e to the x squared d by dx to the n of e to the minus x squared plus e to the x squared. Now you have two terms. One term is going to be where you take zero derivatives. So it's going to be minus 2x on here. So you have this n should now just be 2. N. Sorry. Yeah. All right. So then you start having zero derivatives here, and then you have d by dx to the n of e to the minus x squared. And then you have one derivative on the 2, and so that's going to be minus 2, and it's going to be d by dx to the n minus 1 e to the minus x squared. And I'm missing my choose statements. So n choose 0 is just 1. There's only one way to choose 0 elements. And then n choose 1 should pop out an n there. Let's see. Yeah, okay. So, and now let's start taking a closer look at things. If we look at this term, it's going to be e to the x squared times minus 2x times n derivatives of e to the minus x squared. You notice that lines up exactly with this term here. So that's nice because this term and this term end up canceling. And what you're left with is this guy. And so this becomes -1 to the nth power, and we have a minus sign on it, so let's put an n plus 1. That's going to be n, 2n times d by dx to the n minus 1 power e to the minus x squared. Whew. And, well, that is, or e to the minus 1 squared. Yeah, okay. Yeah. All right, so then we want to make it match up, so we could take a -1 squared out, and so now we're going to have 2n -1 to the n minus 1 d by dx. Here, let me just, I want to rewrite all that, so I'll put this -1 and -1 squared, which is really just 1, right? And so what we end up getting is 2n times hn minus 1 x. I think I lost a term somewhere in here. So we should have had an e to the minus e to the x squared from this guy here. Okay, and so all that together gives us 2n hn minus 1, and yeah, that's nice. And so that, and what was on the other side of that? Well, if we go back here and we take a look, we see that that was the derivative of this guy in one direction here, and then we took the star route over to here. So all this work shows that the derivative of the nth Hermite polynomial is 2n times the n minus first Hermite polynomial. And putting that all together gives us this equation. So we not only have this, but we also have this is equal to 2x hn of x minus 2n hn minus 1 of x. And that is what we set out to prove. So we actually got two equations here, which is pretty nice. There we go. So that's our recursive identity. Okay. Yeah, so that's our Hermite recursion formula and our Hermite for our Hermite polynomials. Okay. Is anybody following along? Any questions? Yeah, maybe we can do that in the next couple weeks. Yeah. Yeah, Laguerre polynomials and Legendre, they're definitely important to talk about. I have a personal affinity for the Hermite polynomials. I just really like them. They show up in RBF type functions, kernel spaces, and also they represent the eigenstates or the eigenfunctions for the quantum harmonic oscillator, which also appears in what is called the Bargmann-Fock space too. So, but yeah, we can talk about all these guys. That'll be a lot of fun. Okay. All right. So that's one guy down. So that's our recursion formula. So we can leverage this recursion formula, and we can get at the generating function for Hermite polynomials. And so, yeah, so Hermite polynomials being related to the Fourier transform, they are intimately related. And so if you take your Hermite polynomials and you multiply them by e to the minus x squared over 2, then that ends up giving you, well, actually, that would change this to be this, and you don't longer get polynomials, but you get these polynomials times a decaying Gaussian. And what those end up being are eigenfunctions for the Fourier transform. I don't think I'm going to be able to get to it today, but I will probably do it next week. And the whole idea is that basically you can leverage the Hermite functions, Hermite polynomials satisfy. Well, no, actually, the Hermite functions. So I'll call them, say, hn of x. And this is a Hermite function times e to the minus x squared over 2. And so hn of x satisfies the minus d squared dx squared plus x squared. Hn is equal to some constant times hn. And so you get this sort of eigenfunction for this differential equation, which is the harmonic oscillator. And because the Fourier transform changes differentiation into multiplication, and so basically we get multiplication by x twice when we take the derivative, when we take the Fourier transform of the derivative, and it takes these guys and it turns them into differentiation on the other side of the Fourier transform. It preserves this differential equation relationship, and because of that, you end up having. You can see that hn of x, you have the same differential equation on the other side of the Fourier transform, and so ultimately what you end up getting is a nice clean transportation using this equation, where you can see that they become eigenfunctions for the Fourier transform. And not only are these eigenfunctions for Fourier transform, but the radon transform will take Hermite functions, and it'll transport Hermite functions to sines and cosines times Hermite functions. And that's really important when you're working with computed tomography and medical imaging. So are these eigenfunctions of the Fourier transform? Yes. If not, what else is there? How do you show it? So I don't know if I'll get to the eigenfunction relationship today, but I'll probably try to do it next week. So they're really, really important, and so and you can also show that these give you these sort of so these also form an orthogonal basis in L2, and with the Hermite functions themselves. And so what you can do is you can actually get an expansion of every function in L2 in terms of these Hermite functions, and Hermite functions also live in the short space. So that relationship also demonstrates that short space functions are dense inside of L2, which is really handy. And so we'll talk about that as we go. Maybe not today. I just want to get these formulas down today, but then we can talk about them in a little bit more deeper level later. If there are more, I'm sorry. Yeah. So okay. The question is, if they are all of the eigenfunctions. Well, in the sense of L2, what you end up getting is that they diagonalize the Fourier transform over L2, because each one of them is an eigenfunction for the Fourier transform. And so if you look at the Fourier transform as an operator over L2 that takes L2 to L2, then that means that they fully diagonalize the Fourier transform. And so then in that sense, they would be complete. And so yeah, I mean, that would be all of the eigenfunctions. Outside of L2, I don't think there are any other eigenfunctions for the Fourier transform, not in any nice clean sense that I can think of. It's hard to say, are there none at all outside of that? Because when you change the vector space that the operator works on, then you change the potential eigenfunctions. But I don't think anything special is going to happen when you change it from L2. So I don't know if that answers your question any better. Sorry if I talk fast. I guess maybe I'm a little nervous. It's been a while since I've done a stream, and streaming has never been something I've been doing very consistently. So let's go ahead and take a look at this generating function. So we're going to have generating function. Yeah. So if you want to look for more general like Fourier transforms and ask those same sort of questions, yeah. But I actually don't do that sort of work very often. I'm very much an applied mathematician. So yeah, I don't have a good clean answer for that one. Let's see. Okay, so basically what we're going to have here is a generating function. So g of xw. So generating functions, I don't know if you guys have worked with them, but basically the whole idea is they have a sequence of something, and you just throw it into a power series. And then the general idea here is to go and try to find a closed form for this generating function, because if you do, then you can basically get at, say, derivatives with respect to w here of g x w. Then that should give you hn of x, and then we set w equals 0. And so then this is how it ends up generating the sequence that you want. And so there's a lot of nice things about generating functions, and they come up a lot in combinatorics and other places. And it's a nice compact way of defining your functions. And so we can go through and work out exactly what this generating function has to be, and that's a lot of fun. Okay, so outside of L2, assume you need to look into L1. Yeah, okay, and these functions are 2. Yeah, right. Yeah. So that makes a lot of sense. I mean, I guess you can take it even further outside of that, and this is where I was having my hesitations, because you can look at this in the setting of like generalized functions too. So you can take a look at tempered distributions and Fourier transforms on that, and I don't think you get any new eigenfunctions in that setting either. Actually, I guess in that setting you have the Schwartz space functions are dense. The regular distributions for Schwartz space that correspond to Schwartz space functions are dense inside of your tempered distributions, and so in that setting too, I don't think you would get anything new. So okay. So as far as I know, as far as like generalizing the Fourier transform to broader and broader classes, I can't think of any other kinds you would get. Okay, so here we're going to start with our recursive formula. So I'm just going to copy this guy. Oop. And copy. Let's move this over. All right. So this is the most useful way to start. You just start with your recursive formula. It's a pretty standard thing to do with generating functions if you haven't seen these before. So we're going to have g of x w is equal to the sum n equals 0 to infinity. Well, okay. So one thing to note is that this recursive formula obviously isn't going to start until n is bigger than or equal to 2, because then you won't have anything to fall back on. So we need to strip out the first two terms. So we're going to have h of 0 of x times 1, and then we're going to have plus h1 of x divided by 1 factorial, so that's just 1, times w. And then we're going to have the rest of our series. So we have sum n equals 2 to infinity of hn of x divided by n factorial w to the n. Okay, and so we end up having this h naught of x plus h1 of x w plus the sum n equals 2 to infinity of, now let's go ahead and replace it in our formula. So we have, say, 2x hn minus 1 of x minus 2 times n minus 1 hn minus 2 of x, all of this divided by n factorial, then w to the n. Okay, and let's see. All right, so we have h naught of x plus h1 xw, and let's start splitting these guys apart. So we have the sum n equals 2 to infinity. We have also the 2x I want to pull out here. So 2x doesn't depend on n, you might as well take it out. So n equals 2 to infinity. We have hn minus 1 of x divided by n factorial, and then this times w to the n. And then we have minus, say, 2, the sum n equals 2 to infinity of n minus 1 h n minus 2 of x divided by n factorial, and w to the n. Okay, so I don't know if you've seen these sort of things before, but essentially what we're trying to do is we're trying to cook up some way of looking at our generating function and trying to find it inside of here. So it's pretty close we're pretty close to having our generating function inside of here. So we have, if this was hn and this was wn and n factorial, well, yeah, we'd be done. It'd basically be our generating function minus a couple terms. Here we have something a little bit off. So what we really want is we would like to have n minus 1 factorial, but since we have an n factorial, this is what we really have. So we have an extra n in here, which is kind of in the way. But, and we also have this w to the n. We would like that to be n minus 1. You could factor out the w, and that would be one way to get at it. Or if we would just take the derivative of this guy, then we have our g of x. And so if I were to go ahead and write a of xw, for instance, as being, say, the sum of n equals 2 to infinity of hn minus 1 of x divided by n factorial omega n, well, if I take the partial derivative with respect to w of axw, then that gives me the sum of hn minus 1 of x divided by n factorial. All right, and then we're going to have n times w to the n minus 1. N equals 2 to infinity. So then what we can do is we can just simplify things, and so we have an n canceling out that n factorial down to an n minus 1 factorial, and so we're going to have the sum n equals 2 to infinity of hn minus 1 of x divided by n minus 1 factorial times w to the n minus 1. And that's practically g of x, g of xw. What only thing we're missing is the first term, because n minus 1 is going to start at index 1, and so it doesn't go all the way back to 2, but we can just write this as g of xw minus 1, because that's what our h naught is. Okay, so we know the derivative of that one gives us this. And so now we have this other guy that we're kind of worried about. And so we basically did this guy. And so let's say put this guy in red, and then that's going to start all of this. All right, so we take derivative of that, we get g of xw minus 1. And now this one we're going to have to do a sort of similar sort of thing. I'm going to take this off to the side. So let me go ahead and copy it. Wonder of tablets. So let's copy. Oops, didn't mean to cut. And let's go ahead and paste it up here. Okay, so this guy, if I call this, say, let's do this work in green, I guess. So this guy, let's call this guy b of xw. And so what we're going to do is I'm also going to take a derivative of this guy. We actually have this weird thing happening. So we have this n minus 1 term on the top there that is going to be taking out a chunk here. So all together on the bottom, we're going to be looking at something as n minus 2 factorial times n after we cancel out this. And so what would be nice, though, is that once we take derivative here, we're going to have that n pop out again, and it's going to cancel this. And so we can get the same sort of stuff happening. So let's go ahead and take a derivative. So if I take the partial derivative with respect to w of b of xw, then that is going to be equal to the sum n equals 2 to infinity of n minus 1 hn minus 2 at x divided by n factorial, and then we get n times wn minus 1. And doing a little bit of finagling, we see that this ends up being n equals 2 to infinity of hn minus 2 of x divided by n minus 2 factorial, and then times w to the n minus 1. This is almost perfect. We're actually starting at the 0th index because n minus 2 at n equals 2 is just 0. And we just have this extra w term in here. And so what we can do is just go and factor out 1w. And so we end up getting w, and change the index. We get n equals 0 to infinity of hn of x divided by n factorial times w to the n. And so this is equal to w times g of xw. So what do we find is that if we take the partial derivative of this guy with respect to w, we end up having an expression in terms of g of xw in these two terms. And so let's go ahead and do that. So we have the partial derivative with respect to w of g of xw is equal to, well, remember we had h naught, which is just 1, and then we had plus h1 time h1 of x times w, and h1 of x is 2x, and so this times w. And now we have this other term that's coming here from a, and so that's going to give us plus 2x. And remember, we're taking the partial derivative with respect to w, so I guess this term went away, and w went away here. And so we have 2x, and then this is g of xw minus 1 for that a term. And then the b term is going to give us minus 2w g of xw. All right, so working this out, we have that 2x here, and then minus that 2x coming from here. So we have this 2x, and then we have 2x times this, and so those both end up canceling. And so we end up having 2x g xw, and then we have minus 2w g xw. And finally, we end up having 2x minus 2w g of xw. Ooh, okay, that's nice. All right, so we're nearly done. So we actually have a nice differential equation in terms of w, and so this quickly tells us that we have g of xw is equal to some, let's say, rho in terms of x times e to the did I make a mistake here? Yeah, 2xw minus w squared. All right, just try and invert the chain rule there. And then you could say, all right, well, what is rho of x? Well, what I can do is I can go ahead and set g of x 0 and see what we should get. And so it's going to just leave rho of x times e to the 0. And so then just it leaves us with rho of x. And we know, on the other hand, that we have it's just going to be giving us the 0th term because all of the w's are attached to everything else. And so we know this is just 1. So that's equal to 1. So we end up getting g of xw then is equal to e to the 2xw minus w squared. And boom, there we go. All right, so that's the generating function relationship, which is pretty nice. Okay, so that's not too bad. Actually getting through these a lot faster than I thought it would. But okay, you guys have any questions while you're hanging out here? Okay. Oh, let's see. What's next on the list? So we've done 2 of those equations, and so we have one more, and then maybe if we have a little bit of time left, we have a little bit more. All right. So for ordinary generating functions, not exponential as you have here, the singularities, the generating function tells you something about the asymptotic behavior of the coefficients. Yep. Yeah, that's true. Yeah, so like for instance, for the Fibonacci sequence, you can pull that out. I think so. I don't work with generating functions a whole lot, to be perfectly honest. But I believe they do tell you some things about the growth. And I mean, if anything, if you just fix x, then you do get a regular generating function just for at that point x. And so, yeah, there's definitely some asymptotics that you can peel out of there. I don't work with it enough to be able to tell you off the top of my head. I do apologize if you're looking for a better answer than that. But yeah, there's definitely going to be some growth behavior you can pull out. That is the worst line I've ever drawn. There we go. Okay. Let's see. All right, so we'll talk about orthogonality. Okay, so one thing I want to mention real quick is kind of important. Sure. All right. Thanks for stopping by. I really appreciate it. All right. Let's see. So we have our hn of x. This we know already is a polynomial, and so it's going to be some coefficient cn times x to the n plus what usually people say lower order terms. And so what we'd like to do is we would like to figure out what that cn is. And that's because that cn is actually going to pop out when we talk about our orthogonality relation, and it'll help us decide how we can turn this into sort of an orthonormal set for L2, for instance. And so what we're going to do is we're going to go ahead and just figure out what that cn is. It's actually not too bad to figure out, to be perfectly honest. So how do I want to go about this? Yeah, so we can use a recursion formula. So in order to get hn of x, we take 2x times hn minus 1 at x, and then minus 2 times n minus 2 hn minus 2x. Did I write that down right? N minus 1. Cool. Right, and so we have that. And so what we can see then is that this guy ends up being a polynomial of degree n minus 2, and this is a polynomial of degree n. And the only difference between hn minus 1 and hn is just multiplying that lead coefficient by 2. So we get this recursion formula. We get cn is equal to 2 times cn minus 1. And, well, we know that c0 is equal to 1. And hence, c1 is equal to 2, c2 is equal to 4, and cn is equal to 2 to the n. All right, so if we go ahead and we take a look at the orthogonality relationship, we want to take a look at hn of x compared to hm of x times e to the minus x squared dx. Integration from minus infinity to infinity. Okay, so what I'm going to do then is I'm going to group one of these guys together, and so I'm going to have the integral from minus infinity to infinity, and we're going to take a look at e to the minus x squared times hn of x times hm of x dx. And we should mention that n I'm going to let be bigger than m in this first setting. So what you end up getting is you end up having this integral from minus infinity to infinity of, let's see, If we use Rodriguez formula, we get -1 to the n. We had an x squared in there that is now annihilated, so this just becomes d by dx to the n times e to the minus x squared. And this guy times hm of x dx. Okay, so now you're left with this. You have this -1 to the n out here. We can pull out -1 to infinity, d by dx to the nth power, e to the minus x squared, and this times hm of x dx. So when you come to this sort of thing, and I should mention that all of these guys are grouped together like this. So we have derivatives of the Gaussian, and we have this times another function. The only way to really move forward in this is to do integration by parts, which allows us to move the derivative off of one and put it onto the other. But one thing that's nice is that, since we're working with a -infinity integration bounds, and we have these Gaussians against polynomials, essentially all the boundary terms just sort of vanish, and we don't have to worry about them at all. And so all we have to do is flip the sign for every time we move a derivative off. And so if we move derivatives over to here and we do this n times, then we come out with a -1 to the n. We're just going to cancel that other -1 to the n. So this guy is equal to e to the minus x squared times d by dx to the n of hm of x dx. And well, now we're taking n derivatives of an m degree polynomial, and we said already that m is smaller than n, and so then this is automatically 0 because it ends up giving us a 0 polynomial. So that's pretty handy. So their actual orthogonality is actually really easy to show. And so what I would like, though, is I ultimately want to turn these into an orthonormal sequence, and that way you can have an orthonormal basis in L2. And so let's take a look and see what that ends up giving us when we have n is equal to m. So we have the integral from -infinity to infinity of hn of x times hn of x times e to the minus x squared over e to the minus x squared dx. And let's see what we end up getting. Okay, so we do the same thing. We end up having grouping e to the minus x squared with one of these terms, and this is going to end up giving us -1 to the n, and then it's going to have d by dx to the n of e to the minus x squared, and then we're going to have this times hn of x dx. Okay, so again, we've used Rodriguez's formula, and we canceled e to the x squared with our e to the minus x squared, and that's pretty nice. And so now I'm going to go ahead and basically do the same trick as before. We're going to move the derivatives onto hn of x. So we get the integral from -infinity to infinity of e to the minus x squared. Then we have n derivatives of hn of x dx. And apologize for my colleagues outside. And then we end up with -1 to the n. Got distracted. So what you end up getting is when you take n derivatives of hn of x, essentially the only thing that's going to survive is the leading coefficient times n factorial. And so we get, so we have the integral -infinity to infinity of e to the minus x squared, and then we're going to have cn times n factorial dx. And, cn we already told you is 2 to the n. We have n factorial, and then the integral from -infinity to infinity of the Gaussian is just the square root of pi. And so that gives us a normalization factor. So if we want to normalize these guys for integration, then what we need to do is we just divide by that, which is pretty nice. Okay, cool. All right, so that's orthogonality. So this is sort of the nuts and bolts of Hermite polynomials, and the whole idea is that you work these out so you can do other sort of arithmetic with them. And so this is sort of the boring stuff. And but it's still kind of fun to figure out and play with. And I plan on making some videos and using this stuff, and I'll just reference the stream later when I want to put stuff together. Let's see, what do we have time for, or what can I even remember doing? So maybe we can take a break on doing some board work and talk about some Matlab stuff. And so I'm an applied mathematician, and so a lot of stuff I do on paper, I also like to transport over to Matlab and do stuff like that there. And so if we hop over to Matlab, let's see. Okay, so this here in Matlab is just some code I threw together, mainly as an example for the class I'm teaching right now. So I'm teaching tomography, and I asked them to do, and one thing that's really nice in tomography is that you have, here, let me actually add a screen here. Actually, let's see. Let's go back to tablet scene. Let's see if I just yank my tablet scene and move it over. So there, that's that one. Copy that. Let's move back over to Matlab. There you go. Okay. So right now I'm teaching a course in tomography, and there's this thing called the radon transform, and the radon transform is pretty important, but it's basically the integral. So the radon transform of a function at t theta is defined to be the integral from minus infinity to infinity of f of t cosine theta plus s sine theta comma t sine theta minus s cosine theta ds. So it's essentially you take a function and you take a line and then you just integrate along this line. And so, oops, let me do that. And so basically this angle here is theta, and this length here is t. And so this is a right angle between them, and so you integrate over that line. What's really cool is that if you take the radon transform of a Hermite polynomial at x times a Hermite polynomial of another degree at m and at e to the minus x squared y squared, then ultimately what this ends up giving you is it gives you cosine to the n of theta sine to the m of theta times h of n plus m at t, and then e to the minus t squared. At least, I'm pretty sure that's what it gives you. I'm just doing this all off the top of my head. Anyway, but the general idea though is that you get this. It lives in your image space, and in the image space, this is where you have what are called sinograms. So you have these sort of like medical imaging type stuff that you get from a CT scanner, and what you can do then is you can go ahead and you can take do some sort of interpolations of this guy in terms of these functions. And once you get those weights, you can do your image reconstruction just by swapping these functions out with these functions, and that should give you a rough idea of, that should give you a pretty good approximation of the original image that you were taking the CT scan of. So this allows you to sort of see inside of a patient that you have inside of a CT scanner without say cutting them open. And so this is one of the tricks that you can do out of medical imaging, and I got it out of this textbook. Well, he didn't do the interpolation, but he used a series of Hermite functions. But this is a book by Stanley Deans. It's Radon Transform and some of his applications. And so this was written about like roughly around the time that the Nobel Prize for CT scanners went out. And that was to Hounsfield and crap, I forgot the other guy. But anyway, it's a really good textbook. I really like it, and it's written by Stanley Deans, who happened to have been a professor of physics here at the university I'm at the University of South Florida, and so it's fun to keep using his textbook in this. This isn't the gold standard textbook though. The gold standard textbook is Natterer's textbook, and that is. That came out around the same time, and it's interesting the difference between these two books. So this book, I mean, it appeals to me as a functional analyst. So I mean, like all my background is in operator theory and functional analysis before I got into a lot of this applied math stuff. And so he talks about things from the perspective of expansions and functional analysis and all these other things. But it was, when it came out, it was just behind the curve. So if you look at the 1970s, one of the things that happened in the 1970s, or especially around the Fourier transforms, is the Cooley and Tukey algorithm, and the fast Fourier transform. And so he doesn't have anything on the fast Fourier transform and anything else like that. And so there's another book that came out, I think, a couple years after this one, and it's by Natterer, and that is considered the Bible of tomography. And the Bible, and in Natterer's book, he has included a lot of work on basically fast Fourier transforms and sampling theory and all those other things, which are very, very practical for actually doing medical imaging and stuff like that. And so whereas I love this book and I love the approach this book takes, and I use it for about half the class that I teach, I eventually switch over to Natterer's book because he includes things about sampling theorems and whatnot. And so Natterer ended up winning out that competition with this textbook, but I think they're both very valuable. But yeah, they're both very cutting edge for their time, though. So the idea of this exercise I have for my students is that, basically what I want them to do is I want them to, I basically do this approximation with the sines and cosines and Hermite functions, but they didn't have any examples of how to make a Hermite function in the class yet. So so I just coded this up real quick, and here I'm using the symbolic toolbox in Matlab. And so I'm going to be doing I'm not doing this approximation, that's their homework, but we're doing this approximation instead. And so I'm going to go ahead and walk you through the code. And I actually recorded myself putting this together, so maybe if I can't get to a stream next week, I'll just release that video, and we can do that. I have more videos I'm producing on Fourier transforms and other things that are coming down the line that are going to be a lot more edited and precise. And so, but yeah, just trying to get back on the train of doing YouTube. All right, so let's see. So it's symbolic toolbox. If you haven't really worked with it before, it's something that's kind of nice inside of Matlab. So I mean, you have a lot of these more dedicated symbolic math packages like Maple and things like that, but I don't find them as easy to code and work with as I find Matlab. So Matlab is great for this. So I have a symbolic variable x, and so the idea of a symbolic variable is that you're telling Matlab that this isn't just some ordinary variable that's just going to hold a value, but this is actually an object that's going to go inside of a function, a polynomial, a power series, something. And so I'm throwing here the assumption that x is also real. And so this variable here is just to tell me how far I want to take my Hermite polynomials, and in this case it's going to be 15 degrees. And so I'm going to go up to, I think it's actually, if I work with Matlab, I'm like, wait, is it start at 0 or is it start at 1? And then do you use braces, or do you use square brackets, or do you use parentheses? Yeah. Anyway, so I have here is I have this diffed Gaussian, and it starts out just being my regular Gaussian. And when I want to make my Hermite function, I just say my Hermite, the first one, and so it's going to be an array of, or a vector in this case. I mean, that's how Matlab thinks. This is a vector of symbolic functions. So diff Gaussian itself is a symbolic function because I use the symbolic variable here inside of this Gaussian, and so I can go ahead and I can multiply it by this other symbolic variable, x squared, e to x squared. And so when these two multiply by each other, you just end up getting the function 1. And so we want to start with this one, and then after that I build on the rest. And so I'm doing this in sort of in another recursive way, just by using this diff Gaussian, taking a derivative more and more of this. So I get diff Gaussian, and I take another derivative of that, and then I throw it in and multiply e to the x squared, and -1 to the n, and then I spool out all, and then this loop here just really spools out all of my Hermite polynomials. And so we can go ahead and just run this portion of the code, and then we can ask to look at what is my Hermite vector. And you can see you have all this stuff. You have 1, you have -2x, and so it's simplified in those cases, but then after this point it stops simplifying. So it has e to x squared, and like, okay, and we end up having this minus 4x squared and all this stuff. And so let's see, so then what the next thing I want to do is I just go through it, and for each one of these guys, I probably don't even need to throw this into a loop, but might as well go through here. And if we call this Hermite thing again, we end up getting this. So we have 1 minus 2x. We have a minus sign in here, so we must be off by like 1. Oh, right. So yeah, so we have like an off by 1 error. So we end up flip-flopping all of our we flipped all of our minus signs, and the reason why is again, so Hermite n is not the nth Hermite polynomial, but it is the n minus 1st polynomial, because h of 0 is this guy, h sub 0, and but this index starts at 1. So then if we go ahead and we try this all again, let's see, boom, paste, let's see what we get. And so Hermite. Okay, so now this is a lot better. So these are just clean polynomials. The simplify command actually told Matlab to look for things it can simplify and remove, and so in this case it removed all of those exponentials that we had here previously, and so I just sort of distributed through and canceled. It's an implicit function inside of Matlab. So now I can just take Hermite polys and just put a value inside of it, and then I end up getting it'll give me this column vector, or this row vector of all my values there. So this was using Rodriguez's formula directly, and it might not be the most computationally efficient way to do it, because taking derivatives even symbolically is pretty taxing on a computer. And so what we could have done instead, and this code does exactly the same thing as I was saying before, is you define the first 2 Hermite polynomials. And so first just x to 0, just because putting in 1, I don't want Matlab to confuse it between a variable and a double. And so that'll just give you the 1 function. And then you get, I put minus 2x, that was stupid, that should have been 2. Anyway, and then that'll give me my first 2 Hermite functions. And then I just push play, and then it'll give me the answer. And this is probably a little bit more efficient than the Rodriguez formula, taking numerical derivatives every single time. But at the end of the day, if you're not computing really huge versions of Hermite polynomials, it's not going to, modern computers handle that pretty fine. Okay, so after we do this Matlab function, we can actually go ahead and see what these all look like. So let's go ahead and take off these comments. All right, so I'm going to go ahead and evaluate this. And it should give me a bunch of Hermite polynomials. And so, let's see, so these aren't normalized. And so they keep growing and growing and growing exponentially. And so this one is probably the 15th polynomial or something like that, based on how big it was. But we can zoom in to these smaller ones and see what they look like. And so, boop. And we can get smaller, dunk, and then smaller. Just funny, the order of magnitude differences. This is why you normalize your functions, kids. But yeah, so these are all my Hermite polynomials, just on -1 to 1. So they do a lot more expressive things as you go further. Let's see. So my idea is I just want to demonstrate how to do some approximations with them. And so in this case, I'm not only wanting to work with just one-dimensional stuff, although we can. I also want to work with 2 dimensions. So in this case, we can do a... let's see. Let's go ahead and hide this stuff. Let's comment this. And yeah, I think all the other stuff should be good. So let's go ahead and plot these. Yeah. All right, so let's go ahead and evaluate that. All right. So here I'm actually plotting 2 different functions. I don't know if it's how easy this is to see. So here, let's try this plot command again. So I'm going to go ahead and plot my original function, f of t, and for the sake of the video, line width, let's make that 3. Whoa. There we go. So nice and bold. And so then the idea is that we'd like to use a certain number of samples in order to recreate this function. And so I'm going to say, let's hold on, and let's plot x sample and y sample, and we'll do this with little circles, and let's make line width 3 here as well. So boom, there you go. So those are my sample sites. And so using these sample sites, we can actually do polynomial interpolation using our Hermite functions. And so then let's see, what we get is we have plot, let's see, t comma z, and let's make this again line width 3. And yeah, so it'll be the new color, whatever that is, when it pops up. So, boom, there we go. So it's pretty close. So we have some issues at the endpoints, at the edges, and that's perfectly normal for interpolation sort of scheme. But overall, this is a pretty good approximation. The function itself, basically had a quadratic in here mixed in with sines and cosines and whatnot. So it wasn't just a polynomial we're trying to interpolate. So we don't expect it to be perfect. And yeah, but it still did pretty good. And the way you do this really is you make an interpolation matrix or a regression matrix, really what this is going to end up being, because we end up taking a pseudo inverse. And so ultimately that ends up being, yeah, sort of a best fit line. So so you just sort of fill in this interpolation matrix with these Hermite polynomials, and basically each row is going to be your Hermite polynomials evaluated as sample, and then you just keep going. You just keep going down, and then you invert it in order to get weights. So it's pretty good. I guess I can write that down. So ultimately, the way this sort of thing works is this. Oop, not that. There. Make this bigger. So ultimately, the way this works is you make a matrix well, okay. So what you want, the goal is you have this f of x, and you're trying to say it is roughly w naught h naught of x plus boom 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 all the way down to w, say capital N of hn at x, right? And so you want to find those w's, and what you have are samples of f. So on this side, you have, say, f of x1, f at x2, all the way down to you have f at xm. And you have your weights, which are w naught down to wn. And so you end up making a linear system here out of all of this. So you have what we want is we want h naught at x1, and then h1 at x1, all the way down until we get to hn at x1. And so this row times, so then we have this row times this column should give us this value. And you want to just keep that going. So h naught of x2, h1 of x2, bop, 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 down to hn at x2. And so then this row times this should give us this guy. And you just keep that going. So you get h naught at xm times h1 at xm, bop, 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 down to hn at xm. And boom, so we get this times this should give you this. Now, if n is equal to m, then this is actually a straight interpolation, and you can invert this matrix. But as long as the xi's are all sort of distinct, and then otherwise you end up with this matrix times w is equal to the samples, and so then if you end up having a sort of rectangular matrix, then you can appeal to just using the more Penrose pseudo inverse. So which basically involves taking the transpose of the matrix, multiplying it on the left, and then you end up getting an invertible matrix, and then you invert it over the other side. And that's if I'd have to sit down and work it out, but basically if you have full column rank, then that gives you an invertible matrix that you can move over. So essentially, collect enough data points until you get full column rank, and then you can invert this, and you'll get w naught through wn. Okay, so that's basically what's going on here. And so let's see. So then what we'd like to do is we'd like to take this and we'd like to move it to 2 dimensions. So we want to do not only 1-dimensional work, but we'd also like to do 2 dimensions. And so there's a trick that you can do in Matlab. And you can take these, here, again, let me just pull up my tablet here. And so what you can do is pretty cool, is you can go ahead and you can take h naught down to hn, capital N, and let's say you want to have this in 2 variables now. So this is just an hx. You can take your 1 variable ones, you can multiply them by each other, and so you get h naught of y down to hn of y, and then doing this ends up giving you all pairwise combinations. So you end up with h naught x times h naught of y, and all the way down until you get h naught at x h n of y, and then keep going. This gives you hn of x hn of y, and yeah, that's pretty cool. So you have and now you have a basis in 2 dimensions, which is really handy. And the same sort of reasoning, this gives you your for L2 of r squared, this would be with the Gaussian weight, this gives you your orthogonal basis. And so we can then take this and we take this square matrix we get out of this guy, and we want to turn it back into a vector. And so that's why we do use this reshape command, reshaping. And then basically we're saying is this? This says for however many rows or columns you need, and then I'm saying I only want one row, column or row. I forget which one's which. I think this is number of rows. So I'm saying let the rows be as big as you need, and just make it all one column. I think that's what we're aiming for here. And in this case, I'm using sort of a standard test for interpolation approximations. It's called the Franke function, and it's built into Matlab. That's how important this thing is. I used to have to code this. I don't know when they inserted it. If I was just dumb at the time and didn't know that it was embedded in Matlab, or if it was more recent inclusion. But I used to have to do it. It's like a whole bunch of different Gaussians. It's a pain in the butt to write up. Anyway, so it's the same stuff that happened before. It's just the way you have to sample things is a little bit different, and you have to use a mesh grid and whatnot. And so I used a ND grid. I didn't use the scattered data approximation. Maybe the week after, and we'll see. But thank you so much, and well, I hope you have a good day. Hold on a second. It's been a while since I've done streaming. I should have like a ending stream thing, shouldn't I? Anyway. All right. Bye. Thank you.